Anybody have homework questions? Yes.
For the last one, I forget what number it is, 2.4, 4B.
I don't know the numbers anymore.
2.44B is to use the monotone convergence series, monotone convergence theorem to supply a proof for the nested interval property that doesn't make use of the AMC. How would you go about doing that? I don't know.
So when I think of the nested intervals, you should imagine like this kind of thing, right? I think I can see a monotone. Monotone means either increasing or decreasing, and bounded sequence. Did anybody else try this one? Do you see any sequence of points which makes a monotone and bounded sequence?
The endpoint?
The endpoints, yeah. Those are the only individual points really that I see at all here. If I look, for instance, just at the left endpoints, they are increasing, aren't they? Because it's nested, right? That means the left endpoints make a sequence which is increasing, and I believe it's bounded just because they're all bounded by like this first right endpoint, right, is greater than all the left endpoints. So by the monotone convergence theorem, the left endpoints, they have to converge to something because they are increasing and bounded. And same goes for the right endpoints. They also have to converge to something. But I think actually it's good enough probably that the left endpoints converge to something. And then you should be able to show that that thing that they converge to, it must be less than all the right endpoints, which means it's in the intersection of everything. So see if you can do something with that. Is that enough to get you going? Maybe. You'll take it?
I need it.
All right. Okay. You could use the right endpoints also. They're decreasing. All right. Great. Okay, let's get down to our business, which is actually we are going to start talking about chapter 3 this time. Chapter 2 also has chapter 2 is mostly about sequences. There's also a discussion about series, although I'm not sure if we're going to get to series in this class. The standard schedule doesn't have series in it, so we'll come back to that if we get to the end with some extra time. But for now, I'm going to move on to chapter 3. Blue here. Chapter 3, which is about, I think it's called Basic Topology of the Real Numbers. Topology of the real numbers. So remember, I don't know if you remember, I don't know if you were listening, I mentioned once this word topology, and we've talked about topological ways of thinking. So far have been thinking about things in terms of neighborhoods, like small sets around points and things like that. We're going to sort of discuss that sort of viewpoint in more detail. And today we're going to start off by talking about open sets and closed sets. Although probably today we'll only be talking about open sets. So let's talk for today at least about open sets. Everybody knows from a young age about open intervals and closed intervals. I don't know how young people are when they first learn about that. I have a 12-year-old. I think she does not know about open intervals and closed intervals. Maybe I'll go home and tell her about them before she learns about them on the playground. Open intervals and closed intervals, though, everybody knows about that. So it turns out, though, there is a more general concept. Any set can be open or closed, not just intervals, but there is a definition for what it means for any set to be open or closed. So let me just remind us of what an open interval is. Open intervals, like this. This is open. Actually, it is an open set also. The definition of open set is meant to encapsulate the same idea as what we mean by open interval. And the idea of an open interval is, well, can I just say this is an open set? I was going to say something a little more in detail here. The closed interval here is not an open set, according to the definitions that we're going to talk about today. Something like this is what they call sometimes like a half open interval or something like that. This is not open or closed. So it is possible to be neither. Something like this, the interval from A up to infinity, an unbounded interval, this, according to our definitions, does still count as an open set. This is an open set. And this is not closed. Something like this, minus infinity to infinity, this is actually open and closed. So the idea, the concepts open and closed, they're not opposites for sets. It is possible for a set to be neither open nor closed, and it's also possible for a set to be open and closed. There's actually a word for that. I'm not making this up. Clopen. Yeah, people really say that. Clopen, it means closed and open, all right? It turns out the entire real number line is both a closed set and also an open set. It is possible to be both. So I still remember something. When I was in college, I took a topology course, and my professor said, sets are not like doors. Doors are either open or closed. A set can be open, it could be closed, it could be neither, or it could be both. All right. Somehow I remembered that slogan. Sets are not like doors. It's true. The basic idea of open versus closed, let's just talk about open for now. They're really two different concepts. It's not like one and the opposite, right? Because you could be both or neither. So you shouldn't really think of them as being two opposing concepts. They are related. But open, for an interval, the idea is basically that it doesn't include its boundary points. Everybody knows that's what open it means in the context of like an open interval. Open means it doesn't include its boundary points. A more useful way to say that for our purposes, I will say, i.e., all points are interior points. Where these words, I know we don't really have definitions for these, but I'm just trying to use these words informally speaking. When I say an open interval doesn't include its boundary points, that's the same as saying in an open interval, none of them are on the boundary. All of them are kind of on the inside, which that sounds a little paradoxical, but I think you will agree that really is true of an open interval, like the open interval from 0 to 1. You could try and sort of draw that. But it is a fact that any point inside the interval is like an inside point. There is no point inside the open interval, which is on the edge, right? Every point is an interior point. No matter how close you pick a point to the 1, it is still on the interior. And what I mean by interior, here comes a real definition. What I mean by interior is you could zoom in on that point and find a little neighborhood around it, which is entirely contained inside the interval. That's what I mean by the word interior. So I'm going to write that as the definition of what an open set is. It means that around every point inside the set, you can put a small neighborhood, which is still contained fully inside the set. So I'm going to say a set. Now here's an interesting thing about our textbook. They actually use a capital O. So that is a O, not a 0. For obvious reasons, people almost never use capital O in math because it looks like a 0. But our book does use the capital O. I'm going to put a little sort of curly hair on it to make it look like an O rather than a 0. You can do whatever you want on your own font. Just don't confuse it with the number 0. So anyway, a set O, a subset of the real numbers, is open if, this is the definition, for every x in O, there is a neighborhood V epsilon of x such that V epsilon of x is a subset of O. All right, this is how you say every point is on the inside. None of the points are on the edge. On the inside means you can always find a little neighborhood around the point which is completely inside the set that you're talking about. All right? If that's always true, then you say the whole set is open. Yeah? There is a neighborhood. I didn't write it out, but I'm usually going to write neighborhood. V epsilon, the epsilon neighborhood of x. All right, so the picture you should have in mind of an open set means your set is like this. This is an open set. What that means is near any point you pick, x, you can always find some small neighborhood around that point, which is completely inside of O, the open set. All right? So, for example, examples of open sets, the interval 0 to 1 is open, right? It's because of what we said before. Any point inside the interval 0 to 1 can always be surrounded by a small neighborhood, which is still inside the interval from 0 to 1. Also, something like, how about, I shouldn't say also, I'm going to say this. This is not open. Since, can anybody say not open? That would mean there is a point which is not on the inside. That is, there is a point which does not have a neighborhood around it, which is completely inside of the set. I'll call this O for now. Can anybody say what's a point which does not have any neighborhood around it? Yeah. 1. Yeah, in this case, I'm going to say since 1 has no neighborhood, V epsilon of 1 with V epsilon of 1 a subset of the interval 0 to 1, like that. All right? And what, the way to think of this on the on a picture is 0 to 1 close at the 1 side. When I look at this point, any small neighborhood, no matter how small, must stretch out past the set. So this leaves O. Any small neighborhood must leave the set. And that violates the definition of open, right? Open means that every point has a small neighborhood around it, which is fully contained inside the set. All right. So that one, 0 to 1, is not open. How about, now I already kind of ruined this. I said, what do you think, 0 all the way to infinity? Is this open? You have to think about what that looks like as a set is 0, not including that point, but it does include just everything else. Is it true that every point in there you can put a little neighborhood around it and it will still be in there? I think that is still true, right? The fact that it goes out to infinity really doesn't change that fact. Just you're taking everything. So this is open. All right. How about here's a cute one. How about the interval 0 to 1 union the interval 2 to 3? So far all I've been talking about are just intervals, but the whole point of what I'm saying here is you can do this for any set, not just intervals. So this looks like that together with that. So this is just a set in 2 pieces. Is that open? What do you think? What you should be thinking of is, if I choose any point in that set, in either the one or the other, doesn't matter, is there a neighborhood around it which never leaves the set? I think the answer is yes. This is open. This is open. Because no matter where you choose your point, let's say I choose it right here, you can always find a little neighborhood around it which is still inside the union, right? Doesn't have to be in both parts, just in one or the other. Okay, so this is open. How about, I'm just trying to go down my favorite subsets of R. How about Q? This one is not very easy to draw, but I might draw it like that. It's sort of, the Q, the rational points are kind of, I suppose, evenly distributed across the whole number line. Is that an open set? You should be asking yourself, if I just choose one of these rationals, can I put a little neighborhood around it which is entirely contained in the rationals? Yeah.
No,
No, why not?
because there's a real number between every rational number and the next rational number.
Yeah, so there are irrationals in between any two rationals. Yeah, that's what he said. Yeah, so Q is not open. It's because if you look at one of these points and you try to make a neighborhood around it, no matter how small your neighborhood is, it automatically will contain some irrationals, which is to say it is not a subset of Q. So any neighborhood, V epsilon, if that point I choose is X, will contain irrationals. Because the irrationals are also evenly sort of dispersed among the reals, all right? Any neighborhood will contain irrationals. So V, this epsilon neighborhood, is not a subset of Q, that would be required. If it was going to be an open set, it means the neighborhood is a subset of the set we're talking about. So Q is not open. All right, how about, maybe I should have done, this is perhaps an easier example. How about N? That would be just these points. Is that an open set? I see some head shakers out there. The answer is no, it is not an open set, because if you try to find little neighborhoods around these points, they will not be contained inside of N, right? This little neighborhood contains many numbers which are not natural numbers. So N is not open. I'm not saying it's closed. Not open is different from closed, right? Closed is a completely different concept. So all of these examples I'm saying are not open. It doesn't mean that they're closed. Actually, some of them are, some of them aren't. But we'll get to that eventually. All right. Any questions up to this point about open sets? All right. I would like to talk for a bit about how can we, oh, did I mention one more important example is all of R. All right. This one is open. That means you just take all the points, and then what does my little neighborhood picture look like? It looks like you just choose some point. Is it true that every little neighborhood will be a subset of R? Yeah. You can always, I shouldn't have said every, although that is true. You can always find a small neighborhood around every real number, which is completely contained inside of R. So that one is open. Okay, what I want to talk about is how does openness relate with unions and intersections? So what if we combine sets using intersection and union? Union. That is, if I have two open sets, I take the union, is the result also an open set? Or if I take the intersection, is the result also an open set? That's what I want to talk about. So for the rest of what I'm going to say here, I'm going to say let A and B be open sets. And the questions I want to answer is A intersect B open? Is A union B open? All right. Let's talk about the union first. If A and B are open, now the simplest case, or the case you should imagine, if I just tell you, hey, think of an open set, what you should imagine in your mind is probably an open interval, because that's like the simplest kind of open set. It's not the only kind of open set, but basically, if someone approaches me on the street and says, hey, I would like you to consider, let A be an open set. In my mind, I will be thinking of an open interval in order to answer whatever question they're about to ask me. That's never happened to me. So what about the union? If you have two open intervals and take the union, is the result still an open set? What do you think? Yeah, actually, we sort of did that a few moments ago. If you do have two open intervals and take the union, the result will be an open set. That should lead you to believe that actually it is true for unions. So for unions, if A and B are open, then A union B is open. It's true. I want to see if we can do a simple little proof of this. We have to demonstrate that A union B is open. So what I want to show is, well, you have to do it like this. Let X be in A union B. Then I want to show for some epsilon greater than 0, V epsilon of X is a subset of A union B, right? This is what it means to show that A union B is open. You choose some point, you have to show that there's some neighborhood of that point which is a subset of the set you are trying to show is open, all right? A union B is like the set O, okay? How are we going to demonstrate this? You have to use the fact that A and B are open. So when I said X is in A union B, how do I convert that into something about A and B? I'll say since X is in A union B, then what does that mean about X and, yeah?
X is in A or X is in B?
Yeah, the union sign sort of logically is very closely related to the or, the word or. Then X is in A or X is in B, right? Now, typically at a point like this, I would try to do the proof in two cases, right? Because I have two options, either X is in A or X is in B. Now, would you believe me if I said the whole proof will read exactly the same way if you do it for X is in A? You just write the same thing again, but change all the A's to B. So I'm going to say there's a little shorthand that mathematicians like to use in such a proof. Maybe you've seen this before. Without loss of generality, let's assume that X is in A. So this phrase, without loss of generality, means I have two options, and you might as well just pick the first option because the second one's going to be entirely the same. We are often going to say that. I will usually abbreviate this like that. Log, without loss of generality, we can assume that X is in A. I'm not saying X really must be in A. It's just either way is the same argument. So we might as well just do it once. We don't have to write the whole thing twice. All right. Without loss of generality, assume X is in A. Then I'm going to say since A is open, there exists some epsilon greater than 0 with V epsilon of X is a subset of A. If A is an open set and X is in A, then you can find a small neighborhood around X, which is part of A, right? That's what A being an open set means. So the idea, the picture that you should have in your mind here is, we have A and B are two different open sets, like in two different pieces. I'm drawing them as if they're intervals, although they might not be intervals, but and then we're just assuming that X is in the A. Let's say this is A and this is B. If X is in the A, the fact that A is open means there is an interval around X, which is inside of A, right? That's what I just said. Since A is open, there exists some small interval around X, which is inside of A. Now, can you find an interval which is inside of A union B? A neighborhood which is inside of A union B? I think actually that same neighborhood is already inside of A union B, right? And so we can just say that. Then what do we got? V epsilon of X is a subset of A, but A itself is a subset of A union B. So V epsilon of X is a subset of A union B. And that's what we needed to show, right? The neighborhood being inside of A it means automatically it's inside of A union B, because A union B is bigger than A. That's how the unions work. All right? Big supporter of unions. Any questions about that? A little political humor for you. All right, let's try the intersections. Can we do that one? So the difference of intersections, at least for the beginning of the proof, really will be exactly the same until we get to this word here. The word or with an intersection needs to change to and, right? Although immediately the rest of the proof will have to be different, but at least the beginning of it will be the same until that point, or. So what about for the intersection? It is also true that the intersection of two open sets is open. So I'm going to try and copy the beginning there. Let X be in A intersection B. Then we'll find epsilon, or I said, sorry, before I start writing the proof, I wanted to write just the statement just so you have it written down. Sorry about this. If A and B are open, then A intersect B is open. That's what we're trying to demonstrate. All right? Okay, now I can start writing the proof. I'm going to say, let X be in A intersect B. And I want to, we'll show that V epsilon of X is a subset of A intersect B for some epsilon. All right? You got to find a small neighborhood. And since X is in A intersect B, then we know X is in A and X is in B. This is the first difference so far. X is in A and X is in B. So the picture you should have in mind for this one is more like, here's my number line. I have two open sets, which I'll imagine them as being intervals. And they have some overlap, like this, right? This is A, this is B. What does A intersect B look like in this picture? Anyone describe in words like on the picture? Yeah.
The overlap.
It's just the overlap. And is that does it look like an open? I think it looks like another open interval, right? It's smaller. So here on the picture, the intersection is like that, right? Okay, great. Do you believe that if I choose a point inside the intersection, you can always find a neighborhood around it? I feel like such a point already must have existed here and here. And in those two sets, it has a neighborhood around it. So maybe that same neighborhood. I don't know, actually, because the neighborhoods up here might be too big once you try to look at them in the smaller picture. But this part of the proof is slightly more tricky. But I'm going to say, since A is open, this point does have a neighborhood inside of A, right? And it also has a neighborhood inside of B, but they might be different sizes because maybe B is a lot smaller than A. The neighborhood in B might have to be a much smaller. But anyway, since A is open, there is a neighborhood, or maybe I'll say there is. Yeah, I'll say it this way. There is a neighborhood. V epsilon, now I'm not going to call it epsilon, I'll call it V epsilon 1 of X, subset of A. And then we get another one from the fact that X is in B and B is open. There's another epsilon. That's what makes this a little more difficult than the previous one. B is open, so there is a neighborhood, another neighborhood. V epsilon 2 of X, which is in B. All right. Really, we need to make one single epsilon neighborhood that will be in both, contained in A and also contained in B. Any thoughts about that? The issue is that one of them might be bigger than the other, right? The A might be this big, whereas the B might be smaller than that. Which one should we choose to be in the intersection? Yeah, Yeah, I think the smaller one, whichever one of those is lesser, and we don't know if it's the A or the B, but whichever one is smaller, that one will be totally contained in the intersection. So I hope that should be clear from the picture. So I'm going to say something like, let epsilon be the minimum of epsilon 1 and epsilon 2. Or you could just say, choose the smaller one as your the epsilon. Then the epsilon of x is a subset of A intersect B. Choose a smaller one, then automatically those neighborhood points, they will be in A, and they will also be in B, which means they are in the intersection A intersect B. All right? That's the end of that. So we've any questions about that? I hope that is sitting in your mind okay. So overall, what we've demonstrated is if A and B are open, then A union B is open, and A intersect B is open. All right. So if you take two open sets, their union is open. If you take two open sets, their intersection is open. What if you want to do this with more than two sets at a time? So what about, A union B union C? Will that be open if A, B, and C are all open? Maybe can I just switch to numbers? How about A1 union A2 union A3? If all those three things are open by themselves, is that union going to be open? Yeah? Can you say why? Without doing the whole proof again? The theorem says if you do just two at a time, then it'll be open.
So like if A1 union A2 is open, then
Right.
you can write it as a single section.
Yeah, so this thing is A1 union A2 union A3 is the same as this, right? There's like an associative property for unions and intersections also. What I'm about to say works for the intersection also. So if you use the theorem, it means this one is open because the theorem is just about two at a time. But then you use the theorem again, and that shows the big one is open, right? Because the theorem tells you the one in parentheses there is open, and then you have that one which is open. The union with the last one, again, will be open because of the theorem. So this business about just combining two sets automatically gets you, so I'll just say loss, I'll say if A1 up to AN, it's not just 3, you can do this for any number. If A1 up to AN are open, then the union, I'll write it this way, union I equals 1 to N of AI is open, and intersection, same thing, I equals 1 to N, AI is open. Right? The sort of, in ordinary words, the slogan that people say for this is any finite union of open sets is open. By finite union, I mean a union of finitely many things. Could be 2 sets, 3 sets, right? And similarly, any finite intersection of open sets is open. All right? This is what we've demonstrated. We really showed it in detail for just 2 sets, but then you can do it for any finite number of sets. All right. What about infinitely many sets? This is an important little detail. This is only what we've said so far. Really, only applies to finitely many sets being combined by unions or intersections. We have seen already that somewhat weird things can happen when you do infinite intersections, as in the nested interval property is about an infinite intersection. How about infinite unions and intersections? By infinite union and infinite intersection, I mean a union of infinitely many things, or an intersection of infinitely many things. Let's look at intersection. Actually, if we intersect infinitely many open sets, the result may not be open. Can anyone give me an example of that? This is something that should refresh or should jog your memory if you think about some examples we did with nested intervals. Can you imagine a bunch of open, you can do this just with intervals, a bunch of open intervals where when you take the intersection of all of them, the result is not open anymore? What do you think? What's your favorite nested intervals? Do you have a favorite nested intervals? If you watched the Bolzano-Weierstrass rap, there was with the illustrated version had some nice diagrams of nested intervals. Although those they don't have to be so complicated as that. I don't know about you. My favorite nested intervals is this. Minus 1 over n to 1 over n. So they look sort of like this. And then the next one, they go minus 1 to 1. Then the next one goes only minus a half to a half. And then minus a third to a third. Like that, right? The space is getting tight. That's what Steve said in one of those verses. I like that line. What's the intersection of this? Intersection of the open intervals minus 1 over n to 1 over n is 0, just the set containing 0. 0 is the only number which is in all of those intervals, the intersection. This is an infinite intersection of open intervals resulting in a single number. Now that's not an open interval, certainly, but that's not even an open set at all. A single number is definitely not an open set because you have to think about, can I put a little neighborhood around that single number such that the whole neighborhood is contained inside this single number again? The answer is no. It's going to stretch out outside of that set. So this, what I have in this example here, these are open, but this over here is not open. Actually, that single point by itself is a closed set, but we don't need to talk about that just yet. Anyway, this example demonstrates, so not all intersections of open sets are open. Not all intersections of open sets are open, right? Only finitely many intersections, then it will be open. But sometimes if you take infinitely many intersections, it will not be open. Another cuter version of this example, you could do something like the intersection of minus 1 over n to 1 plus 1 over n. This way, the left-hand side, as you go down the interval, will sort of shrink up to 0, but the right-hand side will shrink down to only 1. What you get here is the closed interval 0 to 1, which is maybe a cleaner example. You can see clearly an intersection of open sets, which gives you a closed interval, which is not an open set. All right? That's just another example. Okay, so intersections, if you use infinitely many things, an infinite intersection of open sets may not be an open set. All right. What about unions, infinite unions? This will be the last thing on this topic if you feel like we're beginning to get bored with this sort of thing. What about infinite unions? It turns out actually the same proof that was used for finite unions for just two sets will work for infinite unions. I want to see if you guys, we got 10 minutes left. Can we see if you can mimic the proof from a few minutes ago for just the union of two sets? See if you can make it work for any infinite union. So here's the way that this is stated in the book. They write this as a theorem. It says any infinite union of open sets is open. All right. Now, what I mean by an infinite union is, here, I'll get us started. I'm going to say let O, so the notation they use in the book for this, which is kind of fun, so I'll do it the same way. They use the Greek letter lambda, O sub lambda. The open sets. This is kind of like O sub n or O sub I. It's a bunch of different O's, only they use lambda. For every lambda in some set, which they call capital lambda. Capital lambda, a very rare thing to see in mathematics, but it looks like it looks like that when you draw it by hand. If you see it printed, it usually has little feet, little serifs, if you like the terminology. All right, so O lambda is an open set for each lambda in this set, big lambda. The big lambda is called the indexing set. Now, usually when we have infinitely many things, we think of them as being numbered, 1, 2, 3, up to infinity, right? But that actually is specifically only countably many things. If you want even more than that, like an uncountable amount of things, you have to use a different indexing set, not n, but some other set. Anyway, what I want to show is that the union, and the union is written this way. Sorry, my lambdas look a little bit like x's. All right, so I'm going to begin by, I say let x be in this big thing. There, I'll let you try and fill in the blanks from there. Let's try this for about 5 minutes, and then we can talk about it together. Should be able to copy more or less the same ideas as before. I'll give you a hint of where to start if you want. What I just wrote is like the equivalent of the without loss of generality that we did in the old proof. In the old proof, we had just A and B, so X must be in one of those. Here, X is in this giant union. Means X must be in one of those things. right, I guess we should talk about this because we got to go in a few moments. This big union here is playing the role of A union B in the previous sort of smaller version of this proof, right? When I say let X be in the big union, this is where in the old version was just A union B. And then the next step of that, the old proof was, okay, then let's just say that X is in A, and then you say a bunch of stuff. So since X is in the big union, it must be in one of those sets for just one of them. You know, in the previous case, it was either A or B. Here, there's maybe infinitely many different choices, but it's got to be in one of them. So I said, let X be in O sub alpha. I decided to keep it with the Greeks down in the subscripts, but you could call it whatever you want. All right, then I'm going to try and follow the old proof like it said before. So the old proof said, since A is open, then there's some neighborhood, blah, blah, blah. So I'm going to say, since O alpha is open, which it is, we assumed up at the top here that O lambda are open sets for every lambda. So the O alpha is open, then there is some neighborhood, V epsilon of X, which is a subset of O alpha, right? But then this is what it means to be open. And then the end of the old proof will still work in this case. So we can conclude with V epsilon of X is a subset of O alpha, but this is a subset of the giant union of all the O's, right? O alpha is just one of those O's. The big union is all of them put together. So the O alpha is part of that lambda in big lambda. And that's what we wanted, all right? A little tricky. So the moral of the story is all finite intersections of open sets are open, and any unions of open sets are open, finite or infinite. So open sets, there's sort of the topology lingo that people use for this is open sets are closed under finite intersections and arbitrary unions. This word arbitrary means possibly infinite. And closed under is like in the algebraic sense. I'm not talking about closed as in open versus closed. I mean closed under an operation, meaning if you take two things and add them together, the answer is still one of those same kinds of things, right? So if you have two open sets and make a finite, or not two, but any finite number of open sets and make the intersection, it's still open set. And any number at all of open sets, if you take their union, the result is still an open set. Not necessarily finite, any arbitrary union. All right, I guess that'll do it. Next time we'll talk about closed. I hope you're all excited to learn what the word closed means. It's not the opposite of open. See you then.